picking up where we left off on this lecture, how does the effective nuclear charge experienced by the valence electrons of a single atom vary going from left to right across the period of the periodic table? Well, as we already kind of mentioned, it increases, moving from left to right. And you say, why? Well, this is caused by adding more protons and pulling on the shell, I'll just call it. I'll keep that going, of electrons. And just to be clear, constant shielding. So as you're moving across the row, the shielding doesn't change. It's the same electrons from the row above. So electrons within the same shell cannot shield each other. All right, let's do another one. Number 24. Among the nonmetal elements, the change in atomic radius in moving one place left or right in a row is similar than the change in moving one row up or down. Explain these observations. Okay, so I'll grab my little periodic table thing here. So again, among the nonmetal elements, so then when we're talking about the nonmetals, we're just going to hang out over here. The change in atomic radius in moving one place left or right is smaller. I said similar. Is smaller than the change in moving one row up or down. Explain the observations. Okay, so if we're moving left or right, going on, what are we doing over here? Well, we're simply adding a proton, moving from left to right. So that is going to shrink the size of the shell a little bit. What happens as you go from fluorine down to chlorine? You're adding a whole nother shell. And a whole nother shell is going to be a larger effect in comparison to just the shielding going on here. So let's write that down. Moving left or right changes the nuclear charge, which has a lesser effect than adding or subtracting shells. There you go. All right, arrange the following atoms in order of increasing atomic radius based on what we just talked about there. So the ones we're going to be looking at are these guys right here. Aluminum, silicon, gallium, and germanium. So we want to put them of increasing, so smallest first. Which one of these guys should be smallest? Well, these guys up here should be smaller because they have less shells. Of these two, which one should be smaller? Has more effective nuclear charge, so it's going to make the size smaller. So we'll go ahead and write that. So silicon is going to be smaller than aluminum. And then based on the same principle for these two guys, germanium will be smaller than gallium. Easy peasy. That one's done. All right, back to notes. Where were we at with our notes? Looks like we're going on to ionic radius. Okay. Ionic radius trends. I guess that should be a capital T. Okay. And if we do our same kind of periodic table, I'm just going to kind of go like this as a general idea. So it's really going to work the exact same way to an extent. If you take a look in the book, I'm not going to pull that out. You can see it in the lectures, which you may have already looked at. You start off, and again, these are ions. So this is sodium's ion. It has lost an electron, and therefore the shell has gotten smaller because you have more protons than electrons. As you're moving across in this general area, they get smaller because you're losing 2 electrons and 3 electrons, yet the shielding is still the same, so it's going to pull the shell in. But then you do have a little bit of a bounce back when they start gaining electrons. But if you start here over in the non-metals area, that trend still kind of continues over here. As again, you're adding protons to the center, it's still going to pull those shells in. This should be, my scaling isn't great here. But how about this? There we go. And then going down, you still have that trend. That as you're adding shells, these guys are going to get bigger each time. So that works the same over here as well. That these guys will get bigger as you go down the rows. And then compared to across, everything's the same. Okay, let me add a new definition-y kind of thing here, and we'll talk. It's an isoelectronic series. It's a big fancy word. Isoelectronic series. And what that refers to is the number of electrons that the atoms have. So specifically, it is a group of atoms that contain the same amount or number of electrons. And typically, when we have this conversation, we're talking about an octet. 8 electrons on the outside. So a really good example to refer to here is neon. So neon with 10 electrons hanging out here on the outside. You have other atoms that gain and lose electrons to get to the same isoelectronic configuration of neon. So for example, sodium loses 1 of its electrons. It's +1. 10 electrons on the outside. Magnesium loses 2 electrons. +2. 10 electrons. Aluminum loses 3 +3. And then these guys typically will gain electrons and end up with a total of 10 on the outside. So let's kind of write those down as an example. We'll say neon as an example with 10 electrons. Just the example of ones that we have in here. You have nitrogen, typically gains 3 electrons, so -3 compared to neutral. You have oxygen, which typically gains 2 electrons. We have fluorine, typically gains 1. Then you got stable, neutral, neon, and then sodium, +1, magnesium, +2, and aluminum, +3. So all these guys are either gaining or losing electrons to end up in this electron configuration, which is stable for them. Not at all uncommon. As far as the radius, what's going on with the radius with these guys? So the radius will increase or decrease going across. What do you think? what are we doing as you're moving from here? How many protons does nitrogen have? 7, 8, 9, 10, 11, 12, 13. And again, these are protons. So as you're moving from here to here, you're adding more protons on the same shell. So they're all getting to a point where they have the same shell, which is right here, the 8 electrons on the outside. So therefore, the radius is going to decrease as you move left. I'll get there. Left to right across the periodic table, or in this isoelectronic series. All right, good place to end.